Okay, I will repeat. Yeah, thanks a lot. So I shall now, I have to repeat whatever I was saying. What happened? Yeah. Can you see the screen?
Yes. Yes.
Okay. So let me repeat. So during the course of our last lecture, we had this equation, which we had denoted 3 times the double dagger symbol. So this gives the conditional probability density function of Btn plus 1 given Btn equal to Yn is same thing as the probability density function of Btn minus Btn plus 1 minus Btn evaluated at this point. Now here, instead of Tn plus 1, take T, and instead of Tn, take S. And let's say S is less than T. And instead of Yn, you take it as X. So this can be, then that came with this new notation. This is conditional probability density function of Bt given Bs equal to X evaluated at Y is the density function of Bt minus Bs evaluated at Y minus X. So we know that Bt minus Bs has this normal distribution with mean 0 and variance T minus S. But since you have Y minus X there the X acts like a mean. So this expression would mean the density function of the probability density function of the normal distribution with mean at X and variance equal to T minus S evaluated at Y. So that is it. So now we will concentrate today on this function. And we will give it a new name. And you will also see that it is going to have yet another name. Yeah. We are going to call that object transition probability density function of Brownian motion, in the sense that it is the density function of the transition probability of Brownian motion. Okay. So Bt is the standard one-dimensional Brownian motion, and let S and T be time points such that S is strictly less than T and X and Y be real numbers which are fixed. So whatever I was saying, I have just that indicated here. So the conditional probability density function of Bt given Bs equal to X evaluated at Y by that triple this thing, it is the density function of Bt minus Bs at Y minus X. And since we know the density function of Bt minus Bs has the normal distribution with mean 0 and variance T. So mean 0 and variance T, but evaluated at this point. So it is 1 over square root of 2 pi times T minus S, whole thing under square root, multiplied with e to the power minus half Y minus X whole squared divided by T minus S. This is the density function of. So this as a function of Y with all the other things fixed, T, S and X fixed, as a function of Y, this is the probability density function of the normal distribution with mean at X and variance T minus S evaluated at Y. This is a familiar object from your first course in probability. Please note it down. Okay. So note that this object, even though there are these variables are all s, t, y, x are all appearing, this is basically a function of t minus s and y minus x. So basically a function of only t minus s and y minus x. Of course, this is a feature of time homogeneity and spatial homogeneity of the standard Brownian motion. So in spite of this thing here, I mean, we would like to draw a kind of this thing from it for a general situations. So, I mean, which will be useful if you happen to study more general processes, which are generalizations of Brownian motion, what the so-called diffusion processes. Okay. So, I mean, we are not going to introduce any new function. It is just that this function we are going to use in a different, slightly different notation. Yeah. So write as a function of 4 variables. S and X are going to be considered together, and T and Y are going to be considered together. That is why you find a semicolon here. So write it as PSX. So at time point S, the process is at X. And you want to know at time point T, what is the probability of that guy being in a neighborhood of Y. That is the sort of role of the density function, right? So this PSX TY dy is the kind of the volume element of this thing where it will be in a neighborhood of Y at time T. So you write this function. 1 divided by square root of 2 pi minus t minus s, the whole thing, multiplied with e to the power minus of y minus x whole squared divided by t minus x. By the way, at the end of this, I am denoting this equation by a symbol that is the club suit, not club, spade suit. So this function is called the transition probability density function of the standard one-dimensional Brownian. So for example, if A is a Borel set and you integrate this guy with respect to Y over the set A, I mean, let us say A is an interval, AB. So integral A to B of this dy, you are integrating in this variable. That gives you the probability that the Brownian motion Bt is in A, Brownian motion B, the Brownian motion at time point. So Bt is in A given Ps equal to S. So that is the transition probability function. Its density is the transition probability density function. It is a fairly familiar object to you. I'm just writing, I'm going to give a new hat to it. So observe that this is the probability density function of the conditional distribution of Bt given Bs equal to X. So we know that it is the probability density function of a Gaussian distribution. That is a normal, one-dimensional normal distribution. So in probability and statistics, you would have seen this under this avatar, PDF of a Gaussian distribution. I know, you know, by now, the central role played by the normal distribution in probability and statistics. You have some idea. It is also playing a central role in the study of Brownian motion. though we will not have occasion to elaborate on this in this course. Okay. So in particular, if S is 0, X is 0, and then T and Y. So P00 Ty is 1 over square root of 2 pi T, e to the power minus half y squared over 2T. This is the density of the N0T distribution. Now this function, which is denoted by that spade suit, it is a very nice function, though many the trajectories of Brownian motion are fairly possibly can be weird. This is a nice function. In particular, it is not only continuous, it is also differentiable. You can differentiate it quite a few times if you want. Just like in your central limit theorem, whatever may be these things, all the fluctuations, when they are standardized and so on, normalized, and things like that, it follows by central limit theorem, it has a nice probability law. I mean, that only makes many of your statistical procedures possible. In statistics, in many occasions, you will assume that the population is normal. And what is the justification for that assumption? The central limit theorem. So that P is a smooth function in its way. Okay, now look at this function. If you differentiate this with respect to T, and since this guy is a function of T minus S, and of course Y minus X, the derivative with respect to T will be the negative of the derivative with respect to S. And similarly, concerning Y and X. So verify that the partial derivative of the function with respect to S is same thing as negative of the partial derivative of the function with respect to T. And similarly, concerning partial derivative of X with respect to X is negative of the partial derivative of Y. But however, when you differentiate the function with respect to P twice, then 2 times this kind of a minus, this thing happening, that evens out. So the second derivative of P with respect to X is same thing as the second derivative of P with respect to Y. These are very simple verifications. However, don't shirk them. So we had, you remember, we had the 4 variables, we had put S and X in one box, with this thing as a one group, and T and Y as another. And S is strictly less than T. So S and X together can be considered the initial state or the present state of the process. And T and Y may be considered the terminal state or the future state. Yeah, please note it down. You may be now having a feeling about what we are up to in the light of what you have seen earlier concerning continuous time birth death chains and so on. fix S and X and verify that this is a simple calculus exercise for you. As a function of t and y, this function satisfies minus the first derivative of t plus 1/2 the second derivative of t with respect to y evaluated at this point is 0. So del p over del t is equal to half del squared p over del y squared at sx dy is 0. So here s and x act like parameters, act as parameters. The equation is in the variables t and y. So this is a partial differential equation. Do you recognize this equation? Any of you?
Like the heat equation.
It is the heat equation. I mean, of course, if you put this on the other side, this. So those of you who are doing a PDE course, you will recognize this as the heat equation, one of the trinity of, I mean, basic PDE courses, along with the Laplace equation and wave equation. And now that somebody answered, can you, now you have recognized this as the heat equation, can you say something more about this function?
I'm not sure. I'm not taking the PDE course.
Oh, you are not taking. Okay,
Happen to recognize.
okay. Okay. But anyway, it's good that you could recognize this as the heat equation. Okay, first I will write. This is the heat equation. In our context, it is also the forward Kolmogorov equation. So that is why in this symbol, I am looking at the forward direction. Namely, S and X, the initial state is fixed, and this is considered as the equation concerning the terminal state. Yeah. So the forward equation, the initial state Sx is kept fixed, and the evolution of process on S to infinity, on the interval S infinity is described. Not only does this function satisfy the heat equation, so for example, you can consider the following type of problem. Let us say we want to find a function. Let us say the value, say for example, for the sake of illustration, assume that S is equal to 0. Okay, the initial time point is 0. Suppose at time time 0, you know the function which you are seeking. Let us call that as let us say v. V at time 0, it takes it's time 0. Let's say v at time 0 x is some given function g of x. So you want to find v such that it satisfies the heat equation, that is del v over del t, I mean with the minus sign, plus half del squared v over del y squared, is it satisfies the heat equation for all t greater than 0, since we are taking s equal to 0. And v0 at any x, this thing is, let us say the given function g of x. Then it's a result in PDE course, basic PDE course, such a solution can be written as the integral of that g initial value with respect to this density function. Is the integrated with respect to y, of course, taking s equal to 0. In other words, once you have this guy, our good old friend Gaussian density, which is also the transition probability density function of the standard Brownian motion, you are able to generate all the solutions for the initial value problem of the heat equation. So in that context, that our good old Gaussian density is also called the heat kernel. It has got very fundamental connection with the heat equation. And this is the kind of tip of the iceberg, the so-called proverbial tip of the iceberg of the connection between probability and PDE. It has connections with parabolic, that is heat equation is a particular case of what are called parabolic equations. And of course, it also has connections with the elliptic equation, Laplace equation. This object is the one-dimensional Laplacian. Is half of del squared p over del y squared, that operator. So the same object comes as a Gaussian kernel or Gaussian density in probability, basic probability and statistics. It comes as the transition probability density function of an important stochastic process, Brownian motion, in diffusion theory, that is Brownian motion and related processes, that theory, stochastic process theory. And it is also the fundamental solution for the heat equation. Since the solutions for initial value problem can be got out of this function, that function P is also called the fundamental solution. I am not writing all these things because I don't want to load you with terminologies. But it's just I'm saying these things in case some of you decide to look at curious, get curious, you can look at the books. Okay, now that we have got the forward equation, the backward Kolmogorov cannot be far off. Okay, fix the terminal guys, t and y, and show that the function as a function of s and x satisfies this equation. Del p over del s plus half del squared p over del x squared is 0. But here, s is constrained to be less than t. And that the arrow shows backward direction of this. By the way, I think whenever you get a chance, try to attend take a course in PDE and differential equations and so on, because almost, I mean, I may be even at the pain of being contradicted, almost all of analysis has come from trying to understand differential equations, especially partial differential equations. All your functional analysis, all the basic function spaces created, they're all to help out this thing, differential equation, study of PDEs, and some of the ODEs were also created to understand PDEs in simple cases, and integral equations, where differential equation can be studied through certain equivalent integral equations. Integral equations are somewhat easier to study because they are bounded operators. Differential operators generally are unbounded operators. I think you can also look up one of the first books written by Professor Keshavan. I think function, what I mean, first I don't know whether it is called functional analysis and PDE or something. Written very well. Please note it down if you want to. Okay. Now we look at, I mean, this is just, I had initially I had mentioned that Brownian motion has certain esoteric properties. Okay. So basically some sample path, 2 of them I just want to list. Nothing to be proved, of course. These are all beyond the scope of this course. Well, in our description of Brownian motion, we had mentioned that the observations concerning Brownian motion indicate, say in the case of that pollen grain suspended in water, or what we had called as dilute gas and things like that, the movement seems to be haphazard or random. Now, by observing the Brownian motion, that motion for, let us say, a minute or 2 minutes, if you can get an idea of where the in the near future the process would be, what kind of properties from your what you have seen in calculus and things like that might indicate. I'm asking you to venture some guesses. If you are observing something and you can say with certainty it will go, let's say, take for example the simple one-dimensional motion. Suppose you want to say in the next few milliseconds it is going to be, the function will be increasing, the trajectory will be going in a positive direction, increasing or decreasing, things like that. What property can indicate that?
Independent increments, that should be rather low, right? That probability.
No. This I am not want probabilistic property. From your knowledge of calculus and analysis and so on, there is no probability now. It is just that you are observing a path of some motion, some particle, not necessarily Brownian or anything. Something. So, okay, you have, let's say you have observed it for, let's say, about 10 seconds. In the 11th second or 12th second, during that, or even smaller intervals, time intervals, in what kind of will it, the path will sort of go in a, tend to be increasing from what it was earlier or decreasing from what it was earlier? What kind of property will indicate? Use your knowledge of calculus or analysis. Yes?
I'm not sure if I understood your question completely.
Forget about probability theory. Okay? You are observing something moving. Let us say, take for example, simplicity, it is a one-dimensional thing, okay? Yeah, something is moving along certain path or certain curve. Let me not use the word path, okay? What kind of property of that curve will you sort of invoke to say, okay, in the next delta t, the next, that is very small interval, the particle will be, let us say, above its present position or below its present position. I expect one word answer.
Wild guess would be continuity or mean value theorem. Continuity or mean value theorem or something.
Continuity?
Or maybe mean value theorem or something.
Mean value theorem means what? Why do you consider mean value theorem at all? Continuity, will it give you the answer?
Kind of, I think.
Oh, think further. See, what I'm asking is, when can you say that f at x plus delta x will be greater than fx? What kind of
difference? Derivative is positive.
Yes,
Derivative is positive.
derivative is positive. Very good. Differentiability and the derivative is positive, right? Similarly, decreasing means that guy is negative. Okay.
Yeah.
Supposing you are not able to predict that. Let's say the path is continuous. You are not in a position to predict that at all. Would indicate what?
Nowhere differentiable, maybe.
Huh?
Nowhere differentiable.
No, I think you already have seen the answer somewhere. So I didn't expect that kind of an answer. You will not expect that it to be differentiable at that point. It can have a sharp edge, right?
Yeah. Yes.
Can turn very sharply. Since you already know the answer, so I think it is you have perhaps before that, because of that, you have lost the ability to. It will not surprise you what I'm going to say. Okay, so since you have let the cat out of the bag, I might as well state. So for almost all sample parts, is nowhere differential. That is, for any fixed omega, as a function of t, let us say this is nowhere different. It is not differentiable even at a single t. You have heard of examples of functions which are continuous but nowhere differentiable.
Yeah, just stress.
Weierstrass function, right? Now, when you want to study, if you want to study Brownian motion in a rigorous way, what it would amount to is getting hold of an appropriate probability measure on the space of continuous functions. Let us say you are going to study Brownian motion over the interval 0 to 1. Means on the space C01, you know C01 is a nice metric space. It's a complete separable metric space. You also have a norm there, the Banach space, and so on. The uniform norm. So that measure on that space is called the Wiener measure. So what almost everywhere means, with respect to that probability measure, that Wiener measure, for every omega, almost every omega, this guy is nowhere different. In other words, in the space of continuous functions, the Weierstrass type functions form the dominant class in a measure theoretic sense. Something comparable to on the unit interval 0 to 1, you know that the rationals are dense, they are only countable. They are dense. Though they are dense in the sense any other number can be approximated in terms of rationals. With respect to the Lebesgue measure, the irrational numbers just dominate. In 0, 1, the irrational numbers are much more numerous than the rationals. Similarly, the nowhere differentiable functions are the most common things you can find among continuous functions. Smooth functions, etc., though in many cases you can approximate various functions through polynomials and things like that, such functions are, and in some sense, much less.
Can you give an idea of how this Wiener measure will look like? So Lebesgue, it is reasonably okay to visualize, at least
No,
for
unit
intervals.
measure, you have to see the infinite dimensional spaces. We can talk only about probability pairs, basically. Okay. So how the Wiener measure will look like is from that C01, you can take a projection, any coordinate projection will be a map from C01 to R. The Wiener measure under that coordinate projection map will induce the appropriate normal distribution on the real line. And if you take the T1, T2, Tn n time points and take the n-dimensional projection, that is from C01 into Rn, that will give you that measure which will be who's the distribution of BT1, BT2, BTn. So the Wiener measure construction is going in the reverse direction from these things to that. And for that, you have to create the appropriate Borel structure, everything on C01, the appropriate things in a consistent way. There you will have to use what is called Kolmogorov consistency theorem, or let's say the various these things, I mean, improvements using Kolmogorov consistency theorem to start. Because you remember any stochastic process, since our human this thing is we can only describe finitely many things at a time. From finitely many sample points or distributions of finite dimensional distributions, we should be able to gain a lot of information. That is why in this thing of study of stochastic process, whether it is Markov chains, continuous time Markov chains, or such processes like Brownian motion and so on, the finite dimensional distributions are the ones given a lot of importance, because those are the ones which is that kind of information only you can hope to get in any situation. You cannot say anything about the distribution at a countable number of time points unless you can have some idea about how that limit from that finite dimensional thing that thing might look like. So which means on this space of continuous functions, you also will have to have a notion of convergence of probability measures and so on. So to study many of these, all those machinery will have to be built up. I'm sure that B.B. Rao's course would have paved a lot in that direction.
Yep.
Yeah. Another, you would have heard of functions of bounded variation. For example, any monotone function is a function of bounded variation. And with respect to monotone functions, let us say increasing function, you can define what are called a Still-J integral. I think you might have done Still-J integral, right? Riemann Still-J integral.
Yes.
Yeah. So Riemann Still-J integral, you can define for with respect to, let us say, with increasing functions, monotone functions, and similarly decreasing. And there is a theorem in analysis, which again you might have seen in your calculus analysis course. Any function of bounded variation can be written as the difference of two monotone functions. So any function, supposing alpha is a function of bounded variation, you can define integrals, let us say integral gx d alpha x for, let's say, bounded continuous functions g. You can define such Still-J type integral. However, this Brownian path sample, this thing is almost every Brownian path is of unbounded variation on every bounded integral. Which means if you have a nice, even a very nice function g on the real line, integral, let us say 0 to t, GS, DBS, that kind of integral, you cannot define. Therefore, what kind of things need to be needed to define such integrals? That will lead you to, first of all, what is called Ito integral, and more generally stochastic integrals. And such integrals also are important to study sample various processes, more general. That is processes which can be built out of Brownian. So these are just two. And for proofs of these statements, more information on Brownian motion, and also connection of Brownian motion with PDEs and so on, especially heat equation and the Dirichlet problem for Laplacian and so on, one-dimensional and higher dimensional. You can look up this Carrot-Zas and Shale, Brownian motion and stochastic. Probably even an online version will be available. So I think that's the end of today's. You want me to go back to any of these slides? I will do that. Okay, otherwise, I think we will stop sharing. And thank you all very much for your patience. And whatever line you may choose, whether it is continuing in maths or statistics or computer science or data science and whatever it is, wish you all the best. And good luck. We will, I think the exam is that the schedule, I think we have already announced. So wish you all luck. Okay.
Thank you very much. I think the third course I've taken with you, and all of them have been increasing in curiosity and interest. So thanks very much for the lovely course. We've had a great time.
I enjoyed teaching about it, though very often the meager audience has been a dampener, but anyway, that seems to be the this thing of things here. Anyway, okay, wish you all good luck.
Thank you very much. So thanks again.
Thank you so much, Professor. Thanks, Professor.